Hello, welcome back to PhysioDesigner Tutorial Series 4. In this tutorial series, we are going to create a model of human upright posture control on PhysioDesigner. In this time, we modify the model too, which includes time-delayed feedback that we created in the previous tutorial, and introduce additive noise in the ankle torque. Let's begin. We were considering the control mechanism of the human quiet standing posture by modeling the human body with an inverted pendulum. Important variables and parameters in the model are shown here. The tilt angle is theta, height to the center of mass is 1 meter, and weight is 60 kilograms. The gravity is 9.81 meter per second square, and T is the ankle torque. Do you remember that there are 5 types of the torques forming the ankle torque? 2 of them are related to the intrinsic mechanical impedance with passive stiffness and viscosity. Their other 2 are active neural feedbacks determined by delay tilt angle and angular velocity. The last one is noise torque. Before going to the Model 3, which includes an intermittent on-off switching PD control, let's expand the Model 2 and add the noise torque and the ankle torque. All parameter values are the same with the Model 2. Except that the noise intensity sigma is 2 in this model. Here, Xi is a normal random process following Gaussian distribution. The modification of the model is quite simple. However, it is better to explain the meaning of the modification before working on PhysioDesigner. What we need to do is to derive the Euler approximation of stochastic differential equations. In general, stochastic differential equations can be written as the top equation. Here, x is an arbitrary vector of dynamical variables, and xi is a normal random process. Sigma is its intensity. In the form of eta stochastic differential equation, the equation can be interpreted as the second equation, where bt represents the Brownian motion. The Euler approximation transforms the equation to the third one. In the equation, k is a number of the time-delay discrete steps, given by delta over delta t, and delta t is a time step, and is equals to tn plus 1 minus tn. And delta b is the random increments of the Wiener process, and equals to b at tn plus 1 minus b at tn. The increments are independent Gaussian random variable with its expectation is 0, and variance is delta t. If we use discrete white Gaussian noise of intensity unity to rewrite the last equation, we need to adjust the intensity of the noise by multiplying by square root of delta t. Hence, replacing the notation of sigma with sigma prime, which is sigma over square root of delta t, we obtain the last form of the equation. If we use 0.001 for delta t, simply stated, it means that we need to consider about 30 times stronger noise intensity. Okay, now let's modify the model on PhysioDesigner. At first, load the Model 2, which we created in the last tutorial, and run a simulation of this model to compare the simulation results with the one of the model including the noise. Let's use 0.001 for the time step. The state converges to the upright posture after a little vibration. Okay, now let's work on PhysioDesigner. Open a physical quantity dialog by selecting Edit Physical Quantity in the context menu. Find physical quantity named Noise. To find it, you can use Search window, then the hit items come to top of the table, so that one can find it easily. Once noise is selected, change its type to variable parameter at the Basic Setting tab, then move to Implementation tab. Random values following Gaussian distribution can be generated by a function called GaussVariate, which takes 2 arguments, that is mean of the Gaussian distribution denoted by mu and variance sigma. We need to divide them by square root of time step as we learned in the beginning of this tutorial. The entry of mu sigma and time step is automatically created, and they are at the bottom of the table. Here let's set 0 to mu, 2 to sigma, and 0.0012 time step. Okay, that's all. Close the dialog. Then, before executing simulation, let's set the default time step for the simulation. Right-click on the white canvas and select Edit Model Preferences. Go to Numerical Config tab. Set 0.001 at a text box labeled Step. Alright. Then save the file as Model 2 Noise. Call Flint for running simulations. Plot data. Now you see very noisy time course. It's rapidly fluctuating around the upright posture. On the phase plane, it makes jagged circular orbits. In this way, notice that the state point always tries to be close to the fixed point, because the fixed point is asymptotic stable, and noise was added to such system. In the modification process, we used a fixed value 0.001 for the time step, which is implemented as a physical quantity. But this is a bit clumsy, because the time step for simulations can be changed on Flint. If a time step which is other than 0.001 is used on Flint, simulations will not be correct anymore. So the time step should be detected automatically in the model. And it is possible, though it is a little bit tricky. If we can calculate a difference between current simulation time and one step previous time, then it would be time step. To do this, firstly, let's create a physical quantity of variable parameter type, and define it as PQ time equals time. Here time is a special physical quantity predefined in the system, which represents the time used in simulations. And then, go to time step physical quantity. Change its type to state, and set 0.001 for the initial value. The implementation is diff time step, time equals 0. This means that PQ time will not change its value. Go to the Extra Implementation tab, select Condition at the definition type, set a condition that time not equals 0. Time step equals PQ time minus delta time of PQ time. Here, delta time is a function to take a value of one step previous time step of the physical quantity in a simulation, which is an argument of the function. By these definitions, the first step of a simulation, the value of time step is the initial value 0.001, but after that the difference of time of adjacent two time steps is calculated and used as the time step, which is consistent with the time step set on Flint. Okay, now let's check the dynamics, save the model, and call Flint. Of course, the result cannot be exactly the same with the previous simulation, because the model includes probabilistic component, but it is statistically same. That's all for this tutorial. Thank you for watching. Hope to see you next time. Bye bye.